Hello, this is Bhairav. This is my fourth video in my series of on astronomy. Today we will be discussing the evolution of low mass stars. Let's jump right into it. First, let me clarify what is meant by a low mass star. A low mass star is any star which is small, which has a mass less than approximately 2.25 times the mass of the sun. Here is an image of a very low mass star, which is what we are going to be discussing first, which is a star with a mass of less than 1/4 the mass of the sun. The example in this image is Proxima Centauri, the nearest star to Earth, as seen from Hubble. So, what will happen to these low mass red dwarf as they age? As when they run out of hydrogen they almost run out of hydrogen to fuse. As all of it is turned to helium, it will become hotter like this. Of course, this is not an actual image, as red dwarfs take so long to run out of hydrogen that no such late stage in the evolution of a red dwarf has ever been encountered. So these are called blue dwarfs, although of course although they actually only become as blue as white. So as the core, hydrogen runs out, and it initiates hydrogen cell fusion. And due to the fact that in a red dwarf, the star's layers do not become more opaque with higher temperature, it becomes bluer to increase its luminosity, unlike other stars which become colder and much bigger. Eventually, a blue dwarf will now run out of hydrogen, and the whole thing will be helium, which is a helium white dwarf. Of course, we haven't encountered any helium white dwarfs made by this process. So let me show you what this looks like on the main sequence. On the main, we're on the HR diagram. So this is a star, for example, and then it goes horizontally like this, and then it becomes a white dwarf. What about more massive stars? Between 1/4 and 2.25 times the mass of the sun. Well, then it becomes more interesting. Note that this mass range includes the sun. So this is a chart for stars from the zero age main sequence, which is in the last video we saw was when the stars started fusing hydrogen and stopped being a pre-main sequence star. So these stars move upwards and sometimes a bit to the right. This is because the star becomes much larger. The surface cools as it becomes larger. Let us see the details of this. So this is for the evolution of a star which is similar to the sun. It is a main sequence star. When it runs out of hydrogen at its core, it will not immediately start fusing hydrogen around the core, but instead will wait until the area around the core is hot enough to fuse hydrogen. This is the subgiant branch. Then, on the red giant branch, the star will begins hydrogen shell fusion. And as the hydrogen shell goes outward, the star becomes more and more bigger. As core becomes smaller and the core become and the helium core, not generating any energy, releases energy when it becomes smaller, and this is what causes a star to become a red giant. Of course, eventually the helium core becomes hot enough to fuse helium. When this happens, it is a helium flash, in which lots of helium at the core fuses, and as the core expands, the rest of the star, the gravitational potential energy required makes the rest of the star smaller. Then it goes to the red clump, and it grow. And in this phase, the helium in the core is fusing until eventually the helium in the core runs out. And now the star has entered the asymptotic giant branch. In the early asymptotic giant branch, the around the core, helium shell fusion occurs. And then, unfortunately, the helium shell runs out of helium to fuse, and so it moves on to thermally pulsing asymptotic giant branch, which thermally pulses as its namesake, because whenever enough helium is made to fuse in helium shell fusion by the hydrogen fusing layer, the helium burns up very quickly and makes the star a lot brighter, but also makes it expand and cool, which stops hydrogen fusion for a moment, where it makes the luminosity of the star go down, and so it thermally pulses and until it finally ejects its outer layers and begins post-asymptotic giant branch evolution. Then, when it ejects all its outer layers here, and beyond this, there is a carbon-oxygen white dwarf from the helium fusion and a planetary nebula from the rest of the star, where it is expanding debris now. Then, of course, then the luminosity, then it goes around here and becomes where and goes somewhere here as a very small, very hot white dwarf. So, in the next video, we will cover the evolution of intermediate mass stars, which is different in several ways, although it is surprising why. Well, see you in the next video then. Bye.